I was nervous before that. Well, I'm sitting right next to the track.
Hello, everyone. I'm Dylan. This is Wade and Steve. We're working on the Amazon Picking Challenge, so we've been doing it for a few months now. Hansel asked us to give a couple months to go until the contest, but Hansel asked us to come and give kind of an overview of where we're at. So Wade's going to kick us off with a little overview of the competition.
All right, so Amazon has selected a variety of products for us to pick from a shelf. And the shelf starts at about 0.78 meters and goes up. So the first challenge is you've got to pick it up here and place it down here in a bin or wherever it is you have the bin, but the bin has to be resting when you start and when you're done. So you can pick up the bin if you want to, but then you have to put it back. And as you can see from the pictures, the products go from the Sublime, this is actually a pencil holder, thank God. When we first saw it, we thought it was a trash can. So you get mesh, glue, Nerf balls. This is or was a 4-pound block of Dove soap. So there's a whole bunch of different sizes, shapes, and colors that you're trying to deal with. So one of the things you have to figure out is, okay, what product am I looking at and how do I grab it? And how many of them are in the bin? How do I get around? So that's part of the challenge. And we decided that we would go ahead and approach that with a Yale hand. And I think Steve's going to talk about that. Steve's going to talk about that a little bit later. So Amazon is sponsoring the challenge, and they bought Kiva a couple years ago, and they've now deployed 15,000 robots in their warehouse. And they're picking something like 6 million products a day, and they're expecting to double that. They only have robots in, I think it's 10 of their 50 centers, and one center has this incredible robo-stow who picks up pallets and moves it from floor to floor to floor. So they are really automating, and so we're going to help them displace another 2,500 workers by going through this process. All right, let's talk a little bit about the shelf. And so 0.78 meters to the bottom, so we'll have a lift that gets us there. And then you have to pick out the 12 holes. Now, they'll tell you what's in the 12 holes, but then you have to reach into your database of objects and get the right file to reference. And then you have to look out through the vision piece and perceive which one it actually is, where it is, and how you're going to grip it. And Dylan's been working quite diligently on how you get in there and get things. So it's pretty simple. Pick and place from 12 bins. You got to pick it without breaking it. You got to put it down without breaking it. And picking bin at the end has to be on the floor when you're done.
Does it start out on the floor?
The bin starts out on the floor. It must.
Cool. So I'll jump in. So that's the kind of the challenge that we're setting out to solve. So we started by kind of trying to model what we want to do in simulation. And what we kind of came up with was a frame that can be raised and lowered like this, and that has an arm attached to it right here. This guy. This is actually an open source arm, which Steve will talk about in a little bit, that we found and built. But the idea was you'd have this frame, and then the frame would move the arm to the correct bin based on whatever the order was, because like Wade said, we know what's in each bin, and then from there we have a camera. So this is actually in the simulation. This is the camera's view, but we have a camera which then would find like the particular object we're trying to grasp, and then the arm would reach out and grab it. We'll talk a little bit more about what software and hardware we're using to make that stuff happen in a little bit. But first, I'm just going to talk about like status of the gantry. So this is the thing that would support moving the arm to the right place. So it started like this in simulation. This was something we did in Gazebo, and then we moved into CAD. And so I kind of like did a lot of this stuff. So I'm using a program called FreeCAD, which is an open source CAD software, curated design. And we kind of modeled it out using 80/20 So like kind of a standard aluminum extrusion kind of building block system. And then for the motion, you can't really see this that closely, but we decided to use lead screws attached to stepper motors, one here and then one at the other base there, for the Z-axis. So if we want the arm to go up, we have two stepper motors that are attached to two lead screws, which are like a long screw. Those turn synchronized, and that raises the platform or lowers the platform based on what we want to do. Then likewise, for moving the arm left and right, we have another lead screw here, which with a stepper motor kind of hanging off the end. So really, we kind of modeled this after existing 3D printers. Like I have a Lulspot TAS4, which has basically not the same design, but a very similar mechanical design. You know, two Z-axis lead screws, and then another one for the X motion. And so we went ahead and kind of purchased all this, what we could, stock from like MasterCar and 80/20 distributors, different places, various places across the internet. But for these empty holes here, where like these parts are floating in air, we're actually still going through the process of designing these pieces in FreeCAD and then printing them. So like for example, I print this part today, and I'm going to bring to the office later. But this is going to go like up here and hold the top of the lead screw. So we're still in the process of like actively designing and printing the remainder of our parts. So we still have some work to do. So to actually like control it and to drive it, to make it go where we want, we're trying to kind of leverage firmware that powers existing open source 3D printers. So there's a couple. There's Marlin, new one we found is Gerbil. We're looking at them both, and so basically the idea there is that we have a normal kind of 3D printer controller board with like stepper drivers on it, and that drive these steppers. We also have micro switches, just like a 3D printer would, to kind of let us do homing. And then this firmware basically handles all that for us. It has homing kind of built in. It has the ability to like send, the controller a position, like in G code, and then it can, travel to that position. So that's kind of our idea for like motion control of the gantry, and we'll talk about that a little bit. So yeah, so we use this different kind of lead screw, which I've never seen before, torque spleen, which is like a really aggressive lead screw. It's really fast apparently, so we'll see how that goes. One thing's like once we actually get this assembled, which we're pretty close, probably hopefully next week, then we'll see if the steppers we have are strong enough to really power like lifting up the rail and So this is a picture of our office. We have a little office in Claremont, actually the Answer Innovation Center, where we're building this. So here's the existing frame. So this is just the 80/20 that we see here, and then on the ground, kind of on the side here, are lead screws and the stuff right here. So we're missing still like the glue pieces to put them together. We have the steppers with the controller board and everything, and Wade's actually working on getting that software working.
And that's the actual shelf.
And this is the shelf, right? So as part of the contest, you could submit a video to ask Amazon to send you a shelf and all the products, and we did that, and they sent one to us. So yeah, so we will be able to practice on the shelf once we have a robot to practice with. So, cool. Steve.
All right, I brought in the clam arm. We've had some problems with this, so let me introduce you to the University of Colorado open source clam arm, or as my students call it, the dead dragon, because they've never seen it move. I have.
We have a video.
Yeah, it really does work. We had to replace one servo because we don't really understand what happened to it. For some reason, it has failed us. So
The one at the base.
Yeah, of course, it's always the biggest one.
Yeah, it had to be the
the
Most
500
important
the $500 one.
So it's developed by the University of Colorado, which they did a pretty nice job with that. The hardware is not the hard part. It's all the translations that it has to go through. It's a 7th degree of freedom. So there's a lot of translations and rotations that's going on. It is open source. So if anybody wants to go make one, feel free to do it. The software operates with the Robotics operating system and the Move It planning framework. So it easily integrates with the stuff that Dylan and Levi are familiar with. And Dylan mentioned Move It before. It's the open motion planning library, and hopefully we can integrate this pretty easily. Levi has had it kind of moving and kind of doing, but one thing they didn't tell you in the instructions was about the orientation of the motors, and that was a real problem. Next slide. 7 degrees of freedom. We have shoulder pan, shoulder pitch, elbow roll, elbow pitch, wrist roll, wrist pitch, gripper roll, and then the gripper joint, and then the gripper itself. So it's modeled after your arm. This base rotates, so that's where everything starts, and then it ends up with the closing of the gripper. We finally got that working. They very kindly have mixed TTL with 485, 485, 485, 485. Way out the end is TTL again. So it's all a serial communications. It's all jumpered together. So you have to take one jumper from here and put it way up there, and then everything else stops a little short. So that's why all these wires are sticking out right now, because they eventually will have to be plugged in and secured properly. Don't go anywhere.
So actually, yeah, and Steve just rebuilt this because we had the servo that went out, but then also we laser cut the Delrin, so the material that's holding it all together is Delrin, it's kind of plastic, and we tried to do it first at the Fab Lab and it didn't work. They were only able to cut acrylic on their laser cutter, so we built it with acrylic, and then we finally joined Maker Place and then we could cut Delrin, and now we have Delrin.
Yeah, the acrylic is really brittle, and when you start putting forces like this, and then these are very, very powerful motors, I was afraid we're going to crack that acrylic because it is so brittle. Delrin is a lot more flexible and can take some punishment. Drawbacks. Open source documentation is poor to non-existent. It was very, very difficult trying to figure out which pieces went where. As you saw the previous slide before, they had the arm extended. You really didn't get the detail as to orientation of motors. Fabrication, typical college, blind fasteners. Some of these, like these right here, there's a nut in the back. Well, how do you put that nut in there? Well, I had to go and super glue the stupid thing and play with that and thread it out because the super glue got in the threads, so that was a mess. So blind fasteners is a real problem. Normal industrial engineer would catch something like that and take care of it.
What does that mean? Fastener you can't see?
Yes, you can't see it. You can't see it, plus there's no way of taking the nut once everything together and putting it in there. It's like, put the nut in there. Well, there's no way for me to get in there. So
the order of assembly is the issue.
Well, they should have tapped the hole.
they should have a tapped hole.
Yeah.
Really is what they should have done. But
Oh, I see.
okay, it's students will take care of that.
Well, I've been built probably a half dozen times
Yeah.
before, you know. So.
Yeah. So, a little bit of super glue here and there took care of that problem. But then you have to let the super glue dry and let it set, and then had to go get a bottom tapper, because if you use a regular cone tapper, It won't go all the way through. It's a mess. And here is my favorite bugaboo. Imperial and metric fasteners? Really? Come on. You know, stick with one or the other. Don't go with both. It really confuses the issue. Fortunately, all the horns that you see, they're all metric. So at least we got it isolated to the horns. But then all the fasteners to go in the side of the Dynamixels, they're all imperial. I don't know why people do
Otherwise
that.
known as English.
Yeah,
Otherwise known as fraction.
right.
Yeah.
Right. There's several different.
440,
Words
632.
Personally, if I was going to do it, I'd go all metric. Metric to me, I teach my kids that, you know, take 476 millimeters and divide by 2, or take 27 and 7/16 divided by 2. Which one are you going to choose? I'm going to choose the metric. However, we do have excellent support from the supplier. They gave us a lot of hints. I know Dylan contacted them in the very beginning, and he says, you know, if you're going to build this, you need this and this and this and this and all this other stuff. So that was very helpful, and they're very responsive. So that helped a lot. Next.
I put this video in.
Oh, cool.
This was a short video. So before I start it, so at the screen there, so the servos are telling the screen what it thinks its positions are. So you can see, obviously, this is before Steve rebuilt the arm. We have some alignment issues with the servos. They're all, and the shoulder servo in this example here was also not working. So it's just going to move. That's all it's really going to do. And like it's reporting to the computer, which is then tracking its pose, basically. Okay.
All right, we're going to move to the Yale Open Hand Project. Again, this is open source from Yale University. It's a gripper. And they have several different types. They've been developing these for many years. Some of them are really, really excellent. I've seen this one in operation where it can just go in and grab something and you can't pull it out of its hand. It's really, really powerful. Again, they use Dynamixels as the motors. So with this big selection we had here, well, which one's the best for us? And we consulted with the current head of the team, Raymond, and he was very kind and responded to us like he's responding to all the other inquiries from the Amazon Picking Challenge contestants. He's a graduate student out there, and he is heading the Open Hand project as it stands right now. He suggested, due to the precision and the grip and the functionality, to choose what is called the M2. Next slide. That's the M2 hand. And what do you mean, uh-oh?
Not assembled yet, huh?
This is an M2 hand. Parts, parts, more parts, parts, parts. I'm telling you, open source, you tend to wear out your printer because you don't know who goes where. But this is it. This is the Yale M2 Open Hand. These eventually, you can see, some of you can probably see this area right here. This is a friction polyurethane. It's good for grabbing things. So plastic would just slide right off, and they conveniently give you a mold. So what you do is you mix up your urethane, you pour it in, let it sit 48 hours, and take these very thin pieces of ABS off, and you have that right there. So, same thing goes with this one, except you see this flexible piece. This allows the movement of this finger, and it's a flexible material. You also have to pour this, and it also has supporting material that you remove, and then it's free to flex. So
Now, how do they flex that? Is that a cable they pull on?
Yeah.
We'll get to that next.
Yeah, okay.
This is an exploded view. You can see there are several parts. They didn't put it together the way I would put it together. These are very thin 3D printed points. And what do you think the strength of that point is right there? The strength of that point there. That will go back to the next slide, the previous slide. That's why you don't see this on here, because it wasn't a very good design. It constantly broke, fell apart. It's just not a good candidate for a 3D printed.
Is that just a cover?
It's just a cover. That's all it is. But they did a
Masking
poor
tape.
design on that. So, okay, go ahead. Okay, how does this thing move? Anybody know what an agonist is? What's an agonist?
It's the opposite of an antagonist.
Great. An agonist
Good save, Ron.
is actually a muscle term that forces your finger to move. So when you flex, you move like this. This is the agonist. And then there's the antagonist, this one. So when you flex like this is the antagonist. This is the one that keeps the stability. So you pull down on this, all this starts going down, this starts moving this way, and that's what makes it close. This guy controls just the very end of the finger. That's all it does. So if you wanted to fully extend this thing, you release the antagonist. With the agonist, you pull it down. And then one of the things they show in the video is they'll have like a coin. And they'll take the thing fully extended like this, and then they'll curl that last knuckle. And that'll flip the coin onto this. And that's all done with this route right here. So it's very, very dexterous. It can pick up very, very small objects. And with the friction padding, it really can pick up, I saw it pick up small pencils, coins. I saw it pick up a 25 millimeter by 25 millimeter IC. It just picked it up, slipped it up friction-wise, and then away it went. So it was pretty cool. So that's how it moves. And if you can imagine, it takes 2 servos to do that. 1 servo there, 1 servo there. So if you looked at your other ones, the one that had all those 4 fingers, guess how many servos were in there? 8. And 8 servos gets really heavy. And it's bad enough that you see this huge boxing glove on the end of some skinny guy's arm. That's the way I describe this. Because this is actually the smaller one.
It's the smallest.
And if you can imagine a bigger one, it would overwhelm this arm. It looked funny.
And the cubby, the bins are pretty small, actually. It's kind of like when we actually built it, we were surprised. Like, we knew the dimensions before, but actually seeing it, it was smaller than we thought.
Yeah. Is that it? Is that the last one? Oh, drawbacks. Everything's in SolidWorks. So if you don't have SolidWorks, sorry, you're out of luck. Many parts are 3D printed. Everything I have here and all the spares, including the ones that broke, are here. So you really get a workout on your 3D printer. Some of the simple parts, like this one, that's 6 hours to print. So you stay up all night watching your printer go. He has a part numbering system, and he tried to explain it to me once before, I still don't understand how he does his part numbering system. It just doesn't make any sense to me. So I have to constantly go back to him and say, okay, for the Dynamixer, you want an A1 T2/M Dynamixer? Is that what you want? Yeah, that's it. What the heck does that mean? And he tried to explain it to me, and forget it. I don't understand. Parts list and drawings do not match. That's again a huge problem. I went through I've got a cabinet full of screws and nuts and all kinds of stuff. And I kept on going, well, this isn't fitting. Did the wrong screw get in my cabinet? No, it didn't. What's going on? Send them an email, get an email back. Oh no, that's wrong on the parts list. You got to use this one. You're dealing with open source. What do you expect? But I am working with him on finding all these problems and saying, hey, how about this? The documentation, especially how to use the CAD tools, how to do what they call the HDM process, that's to make the flex, is really pretty good. Putting it together is a serious issue, and when you're trying to experiment. Also, one of the problems I found in SolidWorks is if you go and hover your mouse over a part, typically it will come up with a file name. Well, the file name's wrong. What happened there? So I don't know if that's me or his problem. I'm not sure. And again, he goes through the same thing. M3 screws by 8 millimeter, and then use a 440 over here. But Raymond has been very, very helpful. I've called him on the phone. He seems to be living in the lab for some reason. Grad student, we expect. He responds to emails even when I am up at 1:30 in the morning and I send an email and suddenly I get a reply. What's going on here? And you see 1:30 back east, it's 4:30. Okay. Yeah, you're a grad student, all right. So this is some of the problems. I'm sure anybody who's used open source, you're familiar with it. Same old problem.
Are you feeding back this?
Yes.
Giving this feedback?
Yes. In fact, I'm a contributor.
Okay.
Finally, I figured out how to contribute on GitHub. Thanks, Dylan,
All
for
right.
showing me
Yeah,
how to do
cool.
that. I
All
know.
right.
I had a hard time with GitHub going, what the heck is all this stuff? So, yeah, I'm a contributor on GitHub now. So I'm feeding back all the changes. You're up.
Thank you. Okay, cool. So last kind of little bit. So now we just want to talk about what we're doing with the software piece. And this part, we kind of did a lot of it in the beginning when we had to get the simulation ready for the presentation. And we've kind of been on the back burner a little bit while we try and figure out the mechanical design. But high level, we're using ROS, which I've talked about a couple times here before. Robot operating system. Has a lot of packages. There's tons of things you can use off the shelf, and that was kind of our goal. We don't want to write any of this stuff from scratch if we can help it. So within ROS, some of the main packages we're using is MoveIt, which is high-level motion planning. So basically, like with the arm, you define the arm with an XML file, what are all the links and joints, whatnot, and then you feed it to MoveIt, and then you feed it a list of, let's say, end effector or joint positions that you'd like the arm to be in, and it will do a calculation. It can provide a trajectory to you, which has over a series of seconds, points for your motors to try to get to, every 5 times a second or something like that, based on the capabilities of your motors. So it basically designs a path through space for all of your joints to go through to end up at your goal.
So it's doing the kinematics for
It's
you.
doing all the inverse kinematics for you.
Does it know about the environment, so it knows to avoid the side of the
Yes, it
shelf?
does. So if you have perception, which we will, then it will feed that into a map that is maintaining of the environment and visualize it. You can look at it in RViz or some visualization suite. and then it'll take that into account in its planning. It uses this data structure called an octomap, which I guess is like some way to say, like, in the space that it knows about what's occupied and what's not. So it'll take that into account. That's move it. So that's where we're working. Like, that's where we hope to, like, once we have the arm in front of the right bin, and we know we use perception to, like, figure out what object we're trying to grasp and to generate the appropriate grasp. Then once we have that grasp, then we say, okay, move it. Like, take our hand there, and then it'll do it for us. So then ROS control is another package which is important. So this is basically like you have to write controllers to tie like whatever your actuators are to something that ROS can understand. And a lot of this stuff actually is prepackaged. So like the Dynamixel, all these Dynamixel servos, someone already wrote that, a Dynamixel control package, so we don't have to do that. But if we want to, for example, move the frame as part of our planning, so previously I said we might move the frame to the bin and then move it to do the motion planning. Well, we could, in theory, like have it all be integrated and just say, like, it doesn't matter where the arm is on, with respect to the bin. You say, okay, the arm's down here. I'm actually going to reach into this top left bin into this particular point, and it'll use not just the arm servos, but the frame servos or the frame motors to get that gripper in the right place. So it has more options. So we're not sure if we're going to do that or not, but if we did, we'd have to write controllers for the steppers, which actually understand G code, not what ROS is speaking. So that would be like the interface between like the controllers and what they know and how ROS can control them.
And you fit in like physical, like how many
You'd feed in
turns per inch.
Well, actually, yeah. So like it would go ROS would feed in like desired joint positions, and it would be modeled like in ROS. It would be modeled as like a prismatic joint, so like a linear actuator. Basically, it wouldn't know it's a lead screw. It wouldn't have any concept of that. It would just know it goes this way, like straight. And so that would be what's coming from ROS for move it. That would get translated to G code by like our custom controller, and then Marlin or like our firmware on the actual device would translate that into turns, like into stepper motor steps. That's the idea. So the clam arm also has its own ROS packages, which is one of the reasons why we chose it in the first place. It was pretty, some guy, actually another team leader at the picking challenge. He has a team too, who did all that stuff, did a pretty good job. So I've been actually helping him with this. This is also open source and on GitHub, so I'm a contributor there too. Talked a little bit about Marlin for the gantry motion. So we're still evaluating that. Wade is looking on that. And then just for collaboration and task management, we use an assortment of tools. So we use Trello, which is like a task planner for like what we're doing right now, what we want to do, like to capture ideas and things like that. And then GitHub, obviously, for our code. And then we have a mailing list, which like try to keep most of the kind of random group communication there. And then like twice a week, we do Google Hangouts where we like do screen shares and show like what we're working on, what's going on. And then I've been doing a lot of FreeCAD work lately, which has been interesting, educational.
What about the state machine behavior stuff?
Oh, I skipped that. Sorry. So Smash. So above Move It and ROS, you need something to like say what the robot should do high level. So that's what Smash does. It lets you define a state machine. It's actually in Python. So you write like Python that says like, here are my states. Here are the transitions between states. So I can either be like moving to a bin, or I could be grasping an object, and then like we'll maintain that for you and handle transitions. So if like at any point like the e-stop gets triggered, you can interrupt whatever behavior is happening in a kind of a consistent way and like do some kind of graceful shutdown maybe or something like that. I've never worked with this, but that's what we're working on now to try to integrate to do the high level control. But yeah, another ROS package. So normally Levi would be talking about perception. He's another member of our team, but his fiance's birthday is tonight, so he decided to be with her instead of with us. Okay. So he's been working on. We have a camera, a depth camera that's kind of like a Kinect. It's a little different. I forget what the actual name is, but it's like a Kinect, but at shorter range. And he's been working on taking like just a normal picture, and there's like the depth and the normal color picture, and then using a variety of perception libraries to like find interesting areas within that. So here he's identified like there's something here, and then like he's kind of they kind of have an idea of the orientation of that object. So the idea is like once you have this, you feed that into some other system which like says, okay, it's a box and it's in this orientation. Let me generate 50 grasps that could work for that box. Like I could go like here, I could go all the way around this way, whatever. You generate a lot of them, you feed all those to move it, and it will say, okay, out of the 50 you gave me, only 5 can are physically possible to move to, because you don't really know that. Like when you're trying to pick up this object, like at that point you don't know what's really like possible physically. And so like you give it a lot of choices, and then move it comes back and says, actually, this one is the best. So this is the input that motion planning. Here's one more. So this is, I think a little bit might have gotten cut off, but I'll put these slides up. So anyway, this is like some of what Levi wants to do kind of in general for the pipeline. Yeah, I'll let him talk to that some other time. This is kind of his thing. And that's it. That's all we have. So yeah, we have if you want to follow our progress, I'll be tweeting at Robomakery as our progress as we kind of get closer and as we go to Seattle. There's about 40 teams that are competing. It's over 3 days at the end of May. So, yeah. Any questions?
Can the arm reach all the way to the back of the compartment in the shelf?
I think it could. I think it's long enough, but I'm not sure it can. I'm not sure it's like dexterous enough, really, because the bins are so small. Like just to like actually get in there.
Especially the size of that gripper.
Right.
Yeah.
Right. So that's kind of why we started thinking about adding the gantry motion to the larger move it planning, because then move it could do a trajectory where it's like kind of coming up and in.
Is smart enough to do that?
I don't know, we'll find out. So move it.
If not, we may have to go back and revisit having X, Y, and Z.
Yeah, like another like kind of in and out motion. So like
And
once
I
it gets
want to plan on that ahead of time, just in case.
move it when it like it's trying to find a path. It like the planer that everyone uses. It's like a random. It basically does like random sampling. So like it says, here's my goal. I'm just gonna do like 100,000 tasks, and like maybe one of them will hit. Just randomly picks basically. I think there's a little smarter than that, but basically, so like you'll end up with paths that are really crazy looking. So like in simulation, it'll move just a little bit, but the arm will go like a really weird way until it gets there. So we'll try that first, but there's some other planning libraries that you can try also.
How's the winner selected?
So there's a whole point system based on basically the run is a 20-minute time period. At the beginning, you get a JSON file that says like, here's the order, here's 20 items or whatever that you need to fulfill into this bin, and you already know what's in all the bin, the shelves. So you get different points for different objects. So if there's like a bin that has more than one type of object, like there's different things in there, then you get more points for picking that object versus like a bin that just has one thing. Because you already know like what's in the shelf. If it says toothpaste and you know toothpaste is in a bin by itself, in bin 1 by itself, then you just go to bin 1, you pick whatever the thing sees. You don't have to do like distinguish anything. So yeah, so you get points for that. You get points taken away for dropping things. And then if like there's a tie, I guess it goes to time, like who picks them in the fastest amount of time.
Was there a requirement to like
No.
Strange. Anything you want.
Yeah, could you guys explore that?
We looked at vacuums. Yeah.
Oh, UPC. Instead of image and processing, pick up the UPC a little bit.
Oh yeah. Yeah. I mean, I think they're trying to push the vision thing, just because how they do business. So like Amazon, because they have all these robot shelves, they don't like all the shelves have totally different things in them. So they don't really like scan everything and keep it all together. It's all willy-nilly everywhere. So for their particular use case, they need people to visually like see what it
But
is.
if you saw a UPC on the product, that might be a shortcut.
Yes. Yeah. That would
Possible.
That's difficult to do inside the bins, which are not lit.
Yeah.
Without adding lighting.
Do you have any pressure sensors on the gripper?
No.
So also you just have to determine, you know the size of the object and you try to.
We get
Not
we
to
get
crush it.
feedback from the servo. You know, what's the torque?
So
What
that's-
torque am I feeling right now?
So that's a little bit of it.
Yeah.
Are you happy with the Dynamixels so far?
Well, I mean, yeah, they seem to be doing their job, but like everyone says, you can only run them like at a third of their rated torque. So
They get hot? Or
yeah, they get hot, they burn out. We had one problem. I mean, we had a bum servo which we're sending back, so that wasn't great. But yeah, everyone seems to use them for this kind of.
are they like a couple hundred each, or how what's the
Yeah,
price?
yeah. So this like this one here, this one at the bottom, which is the beefiest one, is $500, and then like most of them are probably like $100 to $200. So yeah, this whole arm costs about $2,000.
To start with, they use Maxon motors inside the servo, which their Maxon motors are top flight. They're the best motors you can buy for their size. If you go and look at the Da Vinci surgical,
They use Max.
they use Maxon. Yeah, it's the absolute best.
Does that
So-
cost significantly more?
Hmm?
Does that cost significantly more?
Yeah, they cost a lot.
So are they geared down? There's a gear reduction
Yes.
in the motor assembly.
Yes, metal gears.
Yeah, we need to grease that once in a while.
So have you tested what's the maximum weight limit on a product you might grab? Is that arm going to be able to grab it?
Good question.
Yeah, we're not sure. They're not heavy. Like
Right.
the heaviest thing I think is probably like a couple pounds.
But theoretically, the gripper can grip something. The gantry will pull it out of there.
Right. Right.
So at least you can retrieve it,
Right.
get it out.
I'm not too worried about the gripper. I mean, that gripper will rip your finger off if you want it to. I'm worried about the arm being able to hold it at a distance.
Yeah.
And then what effect does that have in the moment on the gantry itself? Is that a
Exactly.
question? Okay.
Yes.
You haven't figured out that.
Gantry looks pretty beefy, right?
Yeah, gantry.
It's pretty big, you know. But the other problem is that it's not at competition height, so we still need to raise it up like 2.5 feet, which I guess we'll have a table or something, but that's not really figured out yet.
Question. I never read anything about the Amazon challenge. I was wondering, what is Amazon's motivation to have this open challenge? Because with their access to resources, why wouldn't they just go out and buy a company that could accomplish this for them? Do you happen to know?
It's really cheap for them.
Right. They are requiring that all teams make all their code open source after the competition. So basically, like anything anybody does, there's like MIT's competing, Berkeley, like all the big computer like robotics schools are competing. A lot of robotics companies are competing. So they all are contributing whatever they do to this.
Is that real time then? So you can go in and steal their ideas?
After the competition.
Oh, after the competition.
But the contest is an indication that it's an unsolved problem, and Amazon is attempting to fuel the
And this is the
energy
first
in their
year.
direction.
Yeah, and they're planning on doing it every year, they say. So
Is there a cash prize for
yes, yeah, you get first prize is 20,000, second prize is 5, third prize is 1.
Is the release of the software only for the winner or everybody?
Everybody that competes. Yeah, they actually got some they're figuring it out. It's their first year, but like there's like a registration deadline for the video to get the shelf. But to send in the video, you had to send in the contest registration form, and they only sent it out like 3 days before the deadline. And it was this like 10-page legal document, like all these things you can't do, and like what Amazon can do, and everything. And like everybody got in an uproar, about like having to figure that out on the weekend, because all these universities are competing and companies, right? So they have to like have their lawyers look at all that stuff. We didn't really have that problem.
It's gonna be a busy month, 2 months.
2 months, yeah. I mean, it's coming together. But yeah, we have a lot to do. Like we were looking at some of the videos from other teams because there's just another video deadline for like travel funds, which we didn't qualify for, unfortunately. But we looked at a lot of other teams, and like a lot of them are starting with working robots. That's a big difference. So like, we didn't mention that. If you wanted to, they'll have available some industrial robots and like existing robots that you can use. So like a PR2, which is like a research robot, $250,000 research robot, or a Baxter, which is another kind of researchy robot, but it has some industrial use too. And then a few other like industrial robots. You can use those if you want. So that's like aimed at labs that have them at they already have a PR2, but you don't have to bring your PR2. You just like go.
You just
to
bring your flash stick.
Exactly. Yeah.
Cool.
Your code. So so like they're very impressive. So yeah, busy 2 months. We'll see.
So what was the motivation as a team? Was it to place? Was it to, hey, this looks like fun, let's just go ahead and do it, see what happens?
Yeah, it's just a learning experience, really. I'm just getting into robotics myself. I've been doing it for about a year and a half now, and it was a good structured way to do that.
Yep.
So yeah, I'm interested in the ROS part of it and the motion planning, but also like starting to work with real hardware because I haven't really done it before. I don't know about you guys.
I just wanted to build
Sound like a really great idea.
Yeah.
I wanted to hang out with guys who had their own 3D printers and or built them.
Yeah, right.
I got here late, so who are you and why, who's the team?
So the team is just a collection of people, volunteers. It's funded by Robomakery, which is my company that I started. It's a robotics company that is making open source robots for people with physical disabilities. So like if you're paralyzed, after this, I'm working on a robot that picks things up off the ground. So like if you drop something, it can pick it up for you, give it back to you. But yeah, it's a brand new company. So this is kind of like a way for me to get more into the space.
So the picking arm was definitely have an application there.
Yeah, and I also want to do a getting things in and out of a cabinet, putting away groceries, taking things out of a cabinet.
How did you have the idea to start a company when you have little experience?
Well, I'm in software. That's like my training. So I'm a software engineer by training. But I got into robotics, and specifically, I have kids. My older son has muscular dystrophy, and he's going to be paralyzed when he grows up. So that kind of like forced me to change industries and start this company.
With the gripper, you mentioned about the antagonist and the agonist. What are those capable of?
They go down to the servo.
Inside the base of the hand.
Steel
Yeah.
cable.
What are they
In the
made of?
base of the hand. There's a couple dynamixel servos.
Steel.
Are they out of like
They sit right here.
a fishing line or a high tension?
Fishing lines, yeah.
Oh, you're
Just like
kidding.
fishing
That's all it is.
I got some
What is it,
real
40
nice
pound
steel
test?
cable.
I think it's 100.
100-pound test.
line? Oh, okay.
Yeah. So they just come up through here. That's the other thing you have to do to the fingers is you have to drill the or ream out the holes for the line to go through, and it goes over several. Oh, it's right here in my hand. It goes over several dowel pins to make the turn, and then there's several pulleys in here also to make the tight turns. These are just like little guides, so you can do a shallow corner, and then the pulleys will do the sharp corners.
And the pulleys are part of the kit, or the parts that you have to do.
Those are McMaster car.
Yeah.
Yeah,
Those
we
for
bought
you.
those from the industrial
That's for you
park.
right here.
Oh, good. You throw those in the part box.
Oh, cool. There's the pulleys.
Holy moly.
I've been like boxes have been arriving in my house like a couple of days for the last like 3 weeks.
When you mentioned about the molding of the spongy gripper friction part, was there any problems with tolerances and stuff like that? Or how is it adhesion to the part itself?
Oh, yes.
Is that glued together?
Oh, I watched a video of them taking it out of the mold and getting the part off that you don't need without any mold release is really going to be a challenge.
Yes. Yeah. But I've done stuff like that before, and I'm not that intimidated
You
by
can
it.
get a Q-tip and some polyvinyl acetate mold release, and you can put it on the parts you don't want it to stick to.
Guess what that does to
But you
this?
still have the hole, right?
Oh, you're kidding me. Polyvinyl acetate? You can drink that stuff.
Yes.
It's really,
It'll soften it.
uh,
It's really not that bad. I've dealt with molds, pouring metal, and mold releases and things like that. I don't see that much of a problem. I mean, I saw the student, actually Raymond, he has a video out that does that, and I said, well, I wouldn't do it that way. I wouldn't do it that. I would not do that.
Yeah.
Like hold a knife towards you, I wouldn't do that. There's several things in there that I would change. So
so just slip
I'm
it.
confident that I can do it.
Why didn't they just have that part, just print the 3D part with flexi material?
I don't think you can. It's a 48-hour cure time. And this
But
stuff,
they have flexible material that they could use.
I don't know. I'm not an expert on
like
3D printers.
Flexible.
You need
Yeah,
two heads
filament.
for the 3D printer. Yeah.
Yeah, I've got a dual head. I've got a dual extruder.
Or two printers or whatever,
Yeah, I don't
But,
really know.
I didn't bring it. A friend of mine just printed. He's printing a project called OpenRC. It's a open source remote control car. He just printed the wheels. I mean, it's flexible. Feels like rubber.
Huh.
I can bring it next time.
Yeah, I'd be interested in that because that might be something I could pass off.
I mean, if you Google FlexiHand, you'll see that they use that
Okay.
in a similar
I mean, for
similar fashion.
I think Ninja Flex is one candidate.
Right.
Yeah, exactly.
Yeah, I've heard about Ninja Flex.
Really good.
Do you add like sand to the urethane to add?
No.
No, so the urethane is friction, correct?
That's why you have two different urethanes. One is for the flex, one is for the friction.
Right.
The
So you
modulus,
just buy the
the
urethane.
modulus is completely different for each one. So, the flex stuff is really soft, and the other stuff's kind of hard. But they'll pick up a coin, so I'm happy with it. We'll see if we can do it. I'm not going to guarantee anything.
So
In fact,
you
we'll have to bring this back up
Well,
and pick up a coin or something.
so what's
we
the
will.
hardest part you're expecting? What's the biggest risk? The whole thing, or?
Time.
Oh my gosh. I don't know. I mean, what am I most worried about now? Probably that the arm won't actually be able to reach into the bin. It's like just physically it's not like tight enough to get in there. And that we'll have to like,
completely
Yeah,
redesign
redesign
the
everything,
entry in order
yeah.
to get the core
Yeah.
XY on the top. Yeah.
Yeah, my big concern is trying to get this
Yeah.
into the bin with a Cheez-Its box right here. You've got about this much space above that Cheez-Its box. Now, how are you going to do that? That's my main
So you're
you
grabbing
really
the
just have
Cheez-It
one
box, right?
sensor, the depth cameras.
Grab the first thing you get.
yeah.
I believe so, yes.
That's cool if you can do it. That's great.
Yeah, and we're trying to figure out now, like, if we're going to mount the camera to, like, this, like, well, this is actually not going to be the final base, but, like, to the base where the arm is, or we've seen some teams, like, put it at the end
Yeah,
of the
right
arm.
in the end is popular, right?
Yeah.
You can do the weight.
Yeah. Or actually, like, somewhere solid on the frame, or even have, we were talking originally about having two cameras, one on the frame, like, it's a fixed position, and then one on the gripper itself. that's like showing us more details.
Yeah,
about
there's
the item.
there's one contestant that has done that.
Yeah.
And I noticed that they had a problem because they cut the video short, but they were going in like this, and I said, "Oh, that camera's going to hit that thing," and then video stopped. So, okay, but you start sticking a camera up there. Now you're limiting your access into that real small area. I was surprised when we got the thing how small those little compartments really were, and I went, "Oh, this could be a problem."
Has anyone seen the Amazon videos of the Kiva robots going and fetching the bins and bringing them to the humans?
Yeah.
This is the last little bit for the humans, just the part to take the thing from the box. And so the rest of the what is it called? The logistics or whatever is all automated largely with these robots. This is the hardest part. Yeah. Exactly.
Yeah.
Is it against the rules to pull out the bin, or your arm has to go in?
The bins are not removable.
Oh, I see.
They're
Yeah.
sitting on top of a Kiva robot.
Oh, okay. Yeah.
And so you have a 10 centimeter distance between anything you have, like your gantry or your arm. So when the robot comes in, you got to, stand back from the subway train so you don't get hit. And then you got to go in and get it. So yeah, you've got separation there.
What about computing? Is it all local, like a PC, or is it can you do on the server cloud thing? Or
No one's asked if you can offload processing to the cloud. I don't think anyone's. We kind of briefly discussed that, but we didn't seem like it was really necessary because we are bringing a desktop basically
right.
that we're just going to plop right down there.
Right,
use.
and it's in a convention center. When's the last time you were in a convention center when,
Got
oops,
Wi-Fi.
by the way, the Wi-Fi wasn't there?
Yeah.
Don't want to have that. On
Yeah,
the
Wi-Fi is iffy in convention centers. Comes and goes.
Sorry. Go
I heard a lot about everything's been about pulling things out of bin. Is there any part of it where you restock the bin? Is that part of the company? Or are they not interested?
Not this year.
Yeah.
Eventually, you got to run out of boxes of paper clips in the bin, and that bin's got to be
Yeah.
stashed for later orders.
Well, Amazon advertises a fully automated factory. If you've got a guy there pulling stuff out or somebody stocking bins, that's not a truly automated factory.
Right.
Go visit some of the car
Picking the arm would
manufacturers.
have to.
I can imagine somebody getting the wrong stuff in one of the bins easily.
Yeah.
And you go ahead and try and pick it, and that's not what's there.
Well, they have multiple unique products per bin, right? It could be 2 or 3 different boxes of randomly different. I mean, it could be a vegetable thing and a router or something, right?
Yeah. Well, one case is Cheez-Its.
These are the only
glue.
items. These are the only items that
Let's
they're
look
going
at
to.
those.
Yeah. There you
So
go.
you've got crayons, you've got Oreos, which we almost ate one night. I can't recall what. There's the glue bottle.
Books.
There's a book
Paperback
in
books.
here somewhere. There's the book.
A couple books.
Nerf balls. So
Is there a bag of potato chips in there too?
I don't recall.
You're not allowed to crush it.
Right, don't crush the Cheez-Its.
Yeah, the hard things are the Cheez-Its box and then the red box on the top. This is actually
Oh,
a big
it's so
box
flimsy.
of it's really flimsy box of coffee stirrers, those really thin straws. There's like 1,000 of them in there, and it's in this very thin cardboard box. I can barely pick it up without.
Those should be heat
It's
shrink
breaking.
though. Covered with heat
Uh-uh.
shrink.
Nope.
No.
Ordered 2 of them. No.
Okay.
The first one I got actually in the mail had
Sure.
opened and there's stir straws everywhere.
Boy.
You order them from Amazon?
What's the
Yes.
red X on those 2 right things?
They are not using those anymore.
Oh.
They were originally, but then they changed.
So
their-
one of those
No
is
raw
like
eggs?
4 1-pound Dove
the
soap bars.
Oh, too heavy.
I think it's an availability issue or something. I don't know.
Soap?
I think it's too heavy.
I know.
I think if they decided to be outside the scope of the arms, that would.
Yeah, I'll bet it's too heavy. And it's especially since it's at the far extreme.
Mhm.
But the Berkeley team, for example, took all these objects and they put them through some lab that they have that took 500 pictures from every angle of each one of all these different kinds of cameras, and they uploaded all that data for any contestant to use. So in theory, we could, we'd hoped to, maybe we still will use that for some of the vision stuff, but
It's the little blue disc in Levi's last slide.
Yeah.
So what's that thing at the top, one over from the
This.
left?
Spark plug.
A spark plug?
Yes,
Yeah.
thank you.
Oh boy.
An HK or something.
I think they went through and picked the worst possible examples. Maybe the stuff they have most problems with
Yeah, I don't know.
for humans. But
Yeah,
maybe
one of the
that
problems
goes-
with a vacuum grip, you grab that Cheez-It bag, you're gonna lose a lot right through the cardboard. So you gotta be careful, and if you apply too much, it's just gonna rip the
And,
Suck a
inside
hole in
out
the-
and put a
yeah,
hole in
yeah.
it.
and the two books aren't shrink wrapped either.
Right, right.
Oh, I thought that was probably the worst thing. Right there.
And they can be like leaning against each other. They're not going to be behind each other, but they could be touching.
But you don't have to pick every one. You can skip some, right? I mean,
Yeah,
you
you
can choose.
could be opportunistic.
No, I
You
think
can
they
choose
give
not
you-
to do certain items.
I
Right.
think they give you a list of what you're supposed to pick.
They do, but within that
Randomly.
list, you can, if you just want to try and maximize what points you think you can get, like maybe we know we're really good at getting the Nerf balls because you just grab onto them and you got them, so we do that first. Or I don't know, you have some kind of priority in there. Give it some idea of what's fun to pick and what's not.
It doesn't have to be in a certain order, does it?
No.
No, I suspect they just give you a subset of the complete list, possibly more than one of the same item.
Yeah.
I'm sure they give you some easy stuff, and then they're gonna work your way up to the hard stuff. There's gonna be hard stuff in there. Like this could potentially be difficult because you gotta kind of grab it from the top. That means you have to get your hand in there, and
What if it's upside down?
if it's upside down, then how are you gonna actually grab it with something like this? I mean, you can only go so wide, and the articulation helps. But if you go to the Yale open hand, you'll notice they're not grabbing a lot of big objects. They're very selective. Like they will grab like a 2-liter Coke can or 2-liter Coke bottle, but it's empty.
Oh,
So, there's deflection in there that you can make a firm grip on. So, they kind of cheat a little bit. Anybody else? Point out the errors before we go up to Seattle. I want to know what's screwed up.
Yeah, we'll come back after. Let you know how it goes.
Yeah, we want to see it in action, right?
Yes. Yes.
assuming there's time.
Yes. Won't fit through the door. That's the only problem.
Oops.
I was gonna ask you about the Dell one. You chose the Dell one because of the high tensile strength plastic for elasticity.
It's not brittle like acrylic is. Acrylic's very, very brittle.
Dell one's one of the tougher plastics.
Yeah. Well, it's more forgiving. It's got better shear strength.
Are
You
there
take a
that many
piece of acrylic
pieces?
and just do this to it, and it'll snap right off.
Are there that many pieces you can't do cast aluminum or machined aluminum
Well, that's
or even steel?
what do we got here? We got these. We've got these. We've got the base. We got the box. That's all it is.
The rest of the parts are 3D printed with ABS.
They're 3D printed, or these are metal.
Oh,
The,
yeah,
the brackets
not
are
horns.
metal.
Yeah.
So yes, you could do
The
it.
stress
in
points are
aluminum.
metal.
Yeah, you
Okay.
easily do it in metal. You'd have to go get that Chinese thing that drills square holes, though. Which is pretty cool. Anybody see that on YouTube?
No, sorry.
A Chinese drill that drills square holes?
I got a Mortise machine.
Really cool. Yeah, well, this
I've
is
seen mortise
aluminum
machines
and
do it.
Right.
steel.
That's it.
Really cool.
It's not just a broach; it actually is spinning.
Yeah, it's a drill.
Interesting.
Yeah, it's the way they move it up and down, and then move it in. It's fascinating to watch. I'd highly recommend seeing that. It's very innovative.
Chinese square drill.
Chinese square drill.
Okay.
Go figure.